Hmm. Got to start the class. There any questions ever? Start. One more thing. Sorry. Class started. I just wanted to test my audio. And okay, it looks like it's working. Right. The reason why I had to test it again is because I'm using wireless mic, but I'm using a regular headset, so I have to make sure the source of both input and the output are set correctly. So I'm gonna put right about to go. So today we'll continue to talk about graphs, and I got the tablet to work. I got it working yesterday in my assembly programming class, but not 100% because I found that if I fold my tablet all the way, and given that I need to do all the encode to transcoding, there's a live stream from both Discord and OBS, and found that the cooling capability of my laptop computer was not enough to keep up with the processing demand. So the processor is fine in terms of processing power, but it just cannot keep up with everything along the way. So today I set up my equipment a little bit differently. There's no problem in terms of cooling it. Right, it is time for class. It is noontime. I know we are not getting the whole class here yet. Okay, think get more than 10 people, including myself, watching voice channel. But I think some people maybe just kind of lurking around, and I'm not sure. Can you watch the live stream without participating in the voice channel? Does anyone know?
I think so, yeah.
Oh, okay, so there may be people just watching the live stream without joining the voice channel. Okay, that's that happening. All right,
Oh,
so
actually, oh, no, never mind. I think they do have to be in the voice.
oh, okay, gotcha. All right. That's what I thought too. People just have to turn off their mic, part. All right. So what I'm doing is I am because I rebooted my computer, so I have the file with me anymore from last class. I am just opening the same file from last time. Okay. So this is my approximation of a graph from last time. We got 4 vertices and D. We got 5 edges, AB, AC, and also CB. And this is a demonstration of what is a path and what is not a path. And then we want to look at the distance. So the distance from the edge, distance of the edge AB 2, and so on. And you can see none of the edges has a negative distance. So that's the only thing that is not allowed is negative value. It can be 0. And we also initialize S to be the set of C. And according to Dijkstra's algorithm, this means C is the destination. only destination. So this is a pretty simple graph to analyze, and it's not going to demonstrate all the really kind of tricky stuff that Dijkstra's algorithm can do, which is finding a path that is not the shortest, and then later on finds a shorter path, and then they can make adjustments accordingly. I don't think this one can illustrate it, but it's okay. Okay, we'll start with this one as an example. So I'm putting the mouse pad to the side so that you cannot see it more. But what I'm doing is I am switching to Zerno. So I got Zerno working again, which is great because I don't want to get a tablet computer and not being able to use it when I tablet feature. So that's interesting because I don't know why the mouse is. Oh, okay, that's because the tool. Okay, operator error. Okay, so we'll go ahead and look at the same graph that we had last time. So we have A, B, D, and D as vertices. Depending on the textbook and depending on the terminology, a lot of times people also call a vertex a node. Okay, so that's a common uh, you know synonym for vertices. And then we draw the edges. So A to B is an edge, A to C edge, B to C edge, edge, and then C to edge as well. And then most of the time, when we want to express the distance of an edge, we just put a number next to an edge when it is quite obvious what it is. So the edge A to B has a 2, A to C has 0.33, B to C is 0, and then B to D is 1000, and then C to D 10. Okay. And vertex C is the only destination vertex. Okay, so I think some of you remember last time I initially made the set as a set with only D in it, which kind of makes sense, right? Because everybody can get to vertex D, so it seems to make sense that vertex D, is a destination. But I intentionally changed that particular set just to see, what happens when not every vertex can get to the destination vertex according to the Dijkstra algorithm. Okay, so do we have any questions about the pictorial representation of a graph? So let me present the alternative. So is there any comparison? Does anyone prefer the non-graphical representation of a graph, at least in this particular case? No one. Okay, not surprising. Okay, so what we are looking at here is this is what we call a planar graph. Okay, Planar, planar. Okay, so a planar graph means it can be represented in 2 dimensions without the edges going over each other. Okay, you can construct graphs that are planar up to a certain point, but after a certain point, graphs can no longer be planar, which means you start to have edges, going over other edges when you want to represent a graph on a dimensional space. So that is when the pictorial representation starts to become inferior. Okay, it starts to become a problem because looking at all the edges flying over each other is not going to be helpful, visually. And that is the point when the more abstract representation, which is looking at the edges as a set of goals and so on, becomes actually more. It makes more sense, okay? Because we are focusing on algorithm to solve the problem. When we look at a graph like this and we want to find the shortest path, it's actually pretty easy, right? I mean, we can just visually see what the shortest path is. Okay, the shortest path from C to D is the CD edge. The shortest path from B to D is going through C first, then go to D, and then the shortest path from A to D is A to C first, and then C to D. So that's actually pretty obvious, okay, because we can just eyeball the entire thing. But eyeballing is great only when we want to check whether an answer is correct or not for simpler graphs. but it's not really useful because after all, this is a computer science class, so we want to have programs find the shortest path instead of relying on eyeball algorithm quotes to find the shortest path. Okay, so what we'll do next is to look at this. Okay, and what we'll do is we'll look at what the algorithm is going to do. So this is going to be somewhat of a challenge, okay, because we have to keep an eye on the algorithm while keeping an eye on graph, and also what I would just call a trace of the algorithm. So the cool part of teaching this online is you guys can all go to the notes, okay, and look at the algorithm itself, okay. So I'm relying on you guys to open up a separate window in your browser just to look at the notes. And to speed up that process, okay, so what I'll do is I'm going to the notes here, and I'm going to the link, and I'm pasting the link, the text channel for today. Here we go. This is the correct channel. So I'm pasting the link into the text channel for today. So you can just click on that and you can scroll to Dijkstra's algorithm, which is section 4. So go straight to Dijkstra's algorithm. So this way you can keep an eye on the algorithm while I try to track down everything. Okay? Does that make sense? Can everybody do this step, or should I display the algorithm somewhere on the screen where it is recorded? Okay, so I'm assuming people are okay with this. I only got confirmation that it's okay to do it this way. So when you watch this video, obviously it's going to be the same deal, right? Because you just have to kind of open up the algorithm separately while you rewatch the video. Okay, so I will do the same thing. I'm gonna pull this screen or pull this window off from the part that is recorded. Um, this is the graphical representation. I'm gonna keep it up like this, and I'm gonna use a spreadsheet, trace the algorithm, basically record what goes on while work on this algorithm. Calc. It, at the end of the lecture, just go ahead and remind me upload the spreadsheet. All right, so spreadsheet, and let me see if I can move the graph all the way to the left hand side, so this way I got more space. Oh, excellent. So this way I have more space for the spreadsheet, so I can actually show more of this. Just want to move it up a little bit so I get more rows out of it. Oh, okay. So keeping an eye on the algorithm. So how many things do we track? I'm not going to track set S because it only has one element, so we can pretty much remember which one is our destination. It is vertex C. We do have Q to keep track of. Okay, so Q is a set of vertices, so we do have to keep track of Q here. We have all the L values, okay, all the individual L values. We only have 4 vertices with, so it's not too difficult to display each one separately. So we're going to have A, B, and these are the L values of these individual vertices. So I'm just going to merge cells, basically say these are the L values of each individual vertex here. Okay, check out that. And one of the more important things that we also have to keep track of is the set E prime, which is the set of all the edges in the solution graph. So we have to keep track of that as well. And in the algorithm, we also have vertex V that we have to track. Vertex V, which is on the second line after the while, it says select V in Q such that blah, blah, blah. Okay, so V is the vertex that we are focusing on in each iteration while loop. So we want to be able to keep track of that as well. So we're going to have one column for lowercase v. That's the vertex, that is the focus of what we are trying to deal with. And then we also have an edge that we have to focus on. So we'll have one column for E as well. Okay, so this is how I'm going to set up, the trace. We have all the individual variables that we might change. Okay, so we'll go ahead and start with the initialization first. Okay, so the initialization, if you look up the algorithm, on the third line down from the top in the algorithm, it says for each v in S, L of v is a 0. In other words, we start with all the destination vertices, and then we say each one has an L value of 0. So that's C itself. Okay, we only have one single destination, or only one vertex identified as a destination at this point. All of the other ones are non-destinations. So we initialize the L values of all the non-destination vertices to infinity. Okay. Um, so if you read the text, which is the fourth line down from the algorithm in the algorithm, it says the L value is basically what is the length of the shortest path discovered up to this point from vertex V a destination. Okay, now in our case, we only have one destination, so it would be the destination. But it doesn't change the meaning of L. L is the length of the shortest path discovered up to this point. So when we're initializing the algorithm, which means we have not um, explored a single edge, okay, we basically can only say that, well, we'll just make the worst case assumption that A is not connected to destination at all, in which case, it has a length of infinity, or the shortest path has a length of infinity because it will never get there. Okay, so that's how we deal with the initialization of the third and the fourth line in the algorithm. And then the fifth line of the initialization says we want Q to start with the same vertex or the same vertices in general as S. But in this case, we have only identified vertex C as our destination. So Q is going to start with just one single vertex of C. Then we move on to the next line, which is the sixth line in the algorithm. It says E prime equals to the empty set, because at this point we do not know whether there's even one single edge that we should put into the solution graph or not. So this is how we initialize all the variables from outside of the loop. Only the loop has to deal with vertex V and also the edge E, so we are not going to deal with those two for now. So do we have any questions up to this point before we get into the while loop? We are covering the first 6 lines of the algorithm at this point. Questions? Right. So now we get to the while line. It says while Q does not equal to empty set. So we look at Q, and it's definitely not an empty set. So we're going to get into the loop. The first line in the loop, in the while loop, it says select V in Q such that blah, 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 blah. Okay, so it is important to know how we select one out of multiple vertices in Q when there are multiple vertices in Q. But right now, we only have one single vertex in Q, so it doesn't really matter. That has to be the one that we choose. So V is now getting the value of C, which is the only vertex in Q for now. And then the next line says Q gets Q minus the set that only has in it. So in other words, we are just removing the vertex that we have selected into V, and we want to get rid of it in Q. So Q is now getting back to a set. Okay? And then the third line down, the while loop, it says for each in, basically for each edge where vertex V is the head of the edge, do the following. So now we have to identify which E we are talking about. So I'm going to use row to identify the E that we want to talk about. So now we want to look at all the incoming edges to vertex C. We got two of them. Okay, we got A to C. We also got B C. It doesn't really matter which one we explore first. So we'll just go ahead and explore AC first. The AC is edge E. And now in the algorithm, are moving on to assume E equals to WV. So now we know that W is actually what we see as A over here. Okay. So if you want, we can have one extra column just to identify what vertex W is. So in this case, vertex W is A. Okay. So now we get to the next line, which is the if line. Okay. So the if line, which is the second line from inside the for each loop, it says, let's go ahead and add L of V and D of E, and we want to see if the sum of those two is less than L of W. So we first look at W. W is A. L of W, which is L of A, is infinity. Okay. So the other side better be not infinity, because you cannot compare infinity and infinity. You cannot see which one is less than. So we have to look at L of W. Okay, so that's one side. So now we have to look at L of V. V is vertex C, and L of C is a 0, plus D of E. So D of E is not visible from the trace itself, but it is instead shown in the graph, in the graphical representation. It is 0.33. So we have 0 plus 0.33 on the left-hand side of the less than comparison. And then we have infinity on the other side. So we are basically asking, is 0.33 less than infinity? And the answer is yes. Okay. So once the answer is yes, then we get into the then branch of the conditional statement, which starts with updating L of W. Once again, W is vertex A, so that means we're going to update L of A from infinity to the sum of L of V, which is L of C, which is 0, plus the distance of the edge AC, which is 0.33. So we're just going to update it with 0.33. This is the only number that, well, the only number, but some of the other ones we also need a width. So that's what we are doing with increasing the width here. So do we have any questions about row 6 of the trace? Why we are updating L of A from infinity to 0.33? Both in terms of following the algorithm and also in terms of understanding the meaning of doing it. I'm gonna sip my coffee while you guys think and try to questions.
It appears that length depends on W being selected as well as V. That clears a, a lot of things up for me. I was wondering how that L function works.
Oh, okay. So the L function is basically tracking the length of the shortest path discovered up to this point from whatever vertex the function is working on, one of the destinations. It doesn't matter which destination. If we have multiple destination vertices, we just need a shortest path to a destination. The shorter, the better. Does that make sense?
Right, yeah.
Okay. All right, so we are now going to move on to the for each line that is inside the then branch of the conditional statement. So we're really just moving down as we go right now. It says, let's look for edges that are coming out of vertex A in this case, and remove all of those in E prime. And we can see that E prime is an empty set. Okay, so there's nothing to do. Okay, good. And then the next line says, let's put W into, oh, excuse me, let's put WV as an edge into E prime. In other words, we're just putting edge E into E prime, and E prime is a set, so we have to make sure that we use set notations here. So now E has one single edge in it, which is AC. What that means is at this point, we think that the edge AC is part of the shortest paths of vertex C in the solution. Okay, now it is quite obvious this is part of the solution of vertex A to get to a destination, but it is not just that. Okay, so the key not just that. because AC can be on the shortest path from some of the other vertices to destination. Not in this case. Okay, in this case, there are no other vertices where the shortest path has to go through the edge AC to get to the destination, but that can potentially happen. Okay, and then the last thing that we have to do is put W into Q, and W is a variable. It stores A at this point, so Q is now going to have A in it. Okay, lower A, because we just changed the L value of vertex A. That is the reason we put it back in. That's the reason why we put it into the set Q, so that we can say, okay, which vertex goes to vertex A, because those vertices can potentially have their L values affected as well. Okay, so that concludes one iteration of the for each loop. So the next question now is, do we have another edge, where it ends up at vertex C? And the answer is yes. Okay, one of the edges to go, that will end up at vertex C is AC, but there's another edge here which is B. Okay, so now we have to go back to the for each loop, and uh, basically look at another edge. This time it is edge B, which means the variable W is just vertex B. And then we ask the same question again. So getting down to the conditional statement, the only conditional statement, it says, if L of V plus D of E is less than L of W, then, okay, it's that line. So we're going to look at that line and look up, what is L of W. W is B in this case, and L of W is infinity. Then we look at L of E plus L of plus D of E. E is C, and we already know L of C is a 0, so we just have to look up the distance of the edge from B to C, and it is a 0. 0 plus 0 is 0. So the question really becomes, is 0 less than infinity? And the answer is true. Okay, so we go into the then branch of the conditional statement again. First thing we do is to update L of B to the sum that we just calculated, which turns out to be 0. And then we have to remove all the outgoing edges from B, from E prime. But you can see that E prime does not have any edges that is going from vertex B, so there's nothing to remove. Okay, and then we move on to the next line, which is adding stuff to E prime. So E prime is now going to contain two edges. Okay, AC in it, EC is also going to be in it. And for the same reason that we add vertex A to Q, we also have to add vertex C, because vertex B also just got its L value changed, and that is the reason why vertex B now added the set Q. So that concludes the second iteration of the for each. Do you have any questions at this point? Questions? All right. So because it is ending the for each loop, and the for each loop is the last statement for the while loop, so we go back to the beginning of the while loop, is asking, is Q empty or not? And the answer is Q is not empty, which means we cannot exit the loop just yet. So now we have to pick the next vertex to examine, okay, that we call vertex. Use the variable V for that particular vertex. So this time we have to be careful, because we got two elements in Q as a set. Which one should we choose? Well, we're going to choose the one that has the smallest L value. So we look at, we evaluate those two. A has an L value of 0.33, B has an L value of 0. So we're going to choose, okay, so vertex, so V as a variable is going to store as a vertex. And this is from the first line in the while loop. The second line of the while loop is going to remove B from the set Q, okay, because we don't want to keep re-exploring the same vertex. So the moment we pick something out of Q explore, we have to remove that from the set Q. So we now look at vertex B. in the algorithm, we are moving on to the for each line. So the for each line is asking, are there any edges where the head or the edge is vertex B? The answer is yes. Okay, there is one, which is AB. So when we look at the edge AB, A is tail of the edge, so A becomes the value of W. So now we have to ask the question in pseudocode. It's asking, let's examine L of V plus D of E and see if it is less than L of W. So we have to look at L of W first. L of W is L of A is 0.33, okay? And then we look at L of E. E is B, and L of E is 0. But the distance of the edge is 2, okay? Because the edge AB has a distance of 2. So we are looking at 0 plus 2 as an alternative, okay? And so we ask, is less than 0.33? The answer is no, okay? As a result, we are not going to perform the then branch of the conditional statement. Then we get back to the for each, say, to basically ask, do we have another edge ending up at vertex B? Well, according to the graph, this is the only incoming edge of vertex B. So we are done with the for each loop. The for each loop is the last item inside the while loop. So we go back to the beginning of the while loop. So now we go back to the while loop and look at Q. Is Q empty? Q is not empty. So that means that we have performed another iteration. Because Q only has one single element at this point, so I don't really have to put too much focus on, oh, let's pick the one that has the smallest L value, because only one element in it. It has to be the one that has the smallest L value amongst all the vertices in Q at this point. So V is now A, or A is the value of, and then we have to remove it from the set Q. So the set Q is now empty. And then we have to look into all the incoming edges of vertex A. So when you look at the graph, A has no incoming edges. Okay, there are no edges where the head is vertex A. So the for each loop has 0 iteration because there's just no edges that this. So now we go back to the beginning of the loop, which is the is Q not empty, and the answer is false. Okay, Q is empty at this point. So this concludes the execution of the algorithm. So when you look at the result of executing Dijkstra's algorithm, the answer or the solution, you can ignore all of the columns except for column F. Column F is the answer of executing this algorithm. So when we conclude the execution of the algorithm, we got two edges in the solution graph, which is AC, BC. So if I want to graphically represent this in the pictorial representation, um, oh, there we go. I was looking for my stylus. Um, so A is part of the solution, BC is the other solution. So if I were to highlight the solution, it would be those two edges. And so that means when you look at the solution, okay, so when you look at G prime, which is the solution, it has vertex A, it has vertex B, vertex, and also vertex D, but it only has two edges. One edge goes from A to C, having a distance of 0.33. The other edge is going from B to C, having a distance of 0, and that's it. Vertex D is still in the graph, but it has no connectivity whatsoever, vertex C or any other vertex C for that matter. Do we have any questions about what the solution looks like after Dijkstra's algorithm is run? Questions? Okay. And the interesting part about this version of Dijkstra's algorithm is it is actually showing you the shortest paths in plural of all the vertices. In other words, for each vertex in the graph, it shows you the shortest path to a destination. And the question is, I don't see any path from D to C. That's exactly the point. Okay, D does not connect to any destination, so there is no path from D to a destination. Therefore, it is just kind of singled out and floating outside of the other graph just by itself. So I'll let you guys kind of look at the solution a little bit, and we can put fresh it back on. I want you guys to kind of just look at this a little bit. I know some portion is going to be highly, yeah, some stuff is outside of the part for column W in a second with of columns, because columns G I a bit narrower, still fit everything. Looking at both the original graph, the solution graph, and also the trace of running Dijkstra's algorithm. I'll let you guys look at this a little bit and see if you guys have any questions while I sip or take another sip of coffee. All right, we got several people typing. You guys can use the voice channels too. Okay, Carol is first question. So I'm watching the YouTube video because I have been cutting out from also cutting out in the.
I did hear you cut out once, Tack, but that's about it.
Okay, so let me just double check a few things. Um, I was messing around a little bit with filtering, but only in OBS. So if you're watching the YouTube one, you might, the beginning of a sentence that I talk, maybe cut out because I think there's maybe 100 milliseconds, before it detects that I'm talking. But that's only applied to uh, OBS. So I'm checking OBS right now, looking at the filters. Yes, it's throughout my sentence. That really should not be happening. So I can turn off all the filtering in. The one is called the noise gate. Basically, when the volume is below a certain level, it does not get through at all. Okay. So YouTube is now quote unquote fixed, and I did not make any changes on Discord. I can look at all the settings again and see if there's anything here that can potentially change that. I have the usual stuff turned on, which is a noise reduction, echo cancellation, and automatic gain control. In Discord, I can turn off noise reduction and echo cancellation. I don't think those would be an issue where I am at this point. So those are both turned off at this point. And Peter said there's no issue. Okay, and I have to go back to William's question here. Okay. Yeah, so Carol, it could be just your connection. I'm not 100% sure. Um, I can look into to see if I can reduce the bandwidth requirement of streaming.
Yeah,
So
I'm hearing a little bit more your voice cutting out.
it should not happen at this point because I just turned off the.
It just happened right then.
Oh, okay. That is kind of odd. Um, Give me a second here. I'm looking at the stats of OBS. So OBS says I have my connection is good so far. I have not lost anything. There are no skipped frames. So if the frames are not skipping, that means the audio should be fine too. So from OBS's perspective, everything seems to be good. Yesterday, I was having issues yesterday, that frames were getting dropped because my processor was overheating. And today I solved that problem, and um, if my processor is not overheating, and underclocking, that should not be an issue anymore. Oh, okay, so I'm cutting out more now. Huh, okay. I'm going back to voice and video and turn echo cancellation back on and noise cancellation back on in Discord only. So I'm not making any changes to YouTube, just changes to Discord. Is that better? Okay, excellent. All right. All right, so now that we got some technical issues handled, I'm going to go back to William's question. Oh, you're welcome. So we're going back to William's question of both AC and BC are solutions. We are looking for the shortest path. Yes. So we are looking for the shortest path, but from every vertex to a destination. So in this case, AC is obviously the solution for vertex A, because vertex A actually has two ways to get to vertex C, which is AC, which is just one single edge, or it can go from A to B and then B to C. But that path is going to have a length of 2, which is not going to be the shorter path. B, on the other hand, only has one path to go to C. So even if this edge has a cost of has a distance of 20,000, it still has to take it because it is the only way for vertex B to get to vertex C. Vertex T basically has no way to get to the only destination, which is C in this case. All right, cool. So are we doing okay so far with this particular example? If there are any other questions, let's go ahead and ask those questions before we move on to something that is a little bit more interesting, where Dijkstra's algorithm. Okay. Oh, okay. I forgot about Alexander's question. Sorry about that. Can you explain why we started with C real quick? Because C is the only destination. The initialization of the algorithm, I'm going to pull the algorithm back up because I think it's easier for us to talk about it when we can see the algorithm. So when we look at the algorithm, the way we initialize set q is we just copy whatever is in set uppercase S to set q, and we can also see how the set S is defined. It is a subset of vertices identified as destinations. So that's why we start off with C. I'm not sure whether that answers the question for Alexander. Mm-hmm. Okay, excellent. All right. So I have one idea. I'm not sure whether it's practical or not. It's for you guys to implement Dijkstra's algorithm in a particular programming language. I don't really care which one you want to use. Just pick one that you think is best suited for this type of thing. Okay. The reason why that might be helpful is when you write this pseudocode into an actual program. Yes, you have to go through a whole lot of debugging and stuff like that, but you would also start to get a much better understanding of what is happening while the algorithm executes. Okay, so um, it can be a useful experience. Okay, so it can be useful, but at the same time, I also understand um, that it is some extra work for you. So it's not an assignment. Okay, it is not an assignment, but I just think that as an activity to help you understand the algorithm, it can be helpful to write a program to do this. Okay, now if not, we can always be the computer to execute the pseudocode. So we become the computer executing the pseudocode. So that's fine too. So there's no need to actually write an actual program to do it. But if you have time and you want to gain a better understanding of the algorithm, I personally think nothing beats writing an algorithm to run it first. Um, it's a little bit different. Um, I have not taught 430, well, not for a long time. I taught it only once, but I do not know which algorithm Iraj uses in that class. If I remember correctly from comments that I got from students from from previous classes, the one that Iraj uses does not handle multiple destination vertices. If anyone is taking that class now or has taken that class already, you can comment on that. While I work on the next graph, because I want to work on a slightly different graph that is a little bit more interesting. Okay, I'm not seeing any feedback from other people. All right, so what I'm doing is I'm trying to construct a graph where one path discovered first is actually not the best path, okay? So to come up with something like this time I'm going to use vertex D. Oh, okay, wrong color. So let me pick the right color here. All right, so we're going to start with a destination vertex. This time we'll start with D, and I'm going to use double circle to identify this is my one of the destinations. We'll make it the only destination for now because we just want to uh, look at the algorithm from the perspective of how do we fix a shortest path when we discover something is actually something else is shorter. Okay, so we'll see one incoming edge that is super attractive. Okay, so let's say vertex C is going to vertex D with a very low distance, a very short distance. Okay, Caro is. Oh, okay. Oh, okay. So they have not talked about Dijkstra's algorithm yet. Okay.
Oh, we
If
actually just got to hashing last session.
Oh, okay. So is it running a little bit behind, or is that kind of normal for that class?
I wouldn't know. I'm guessing a little bit behind, but I
Okay.
wouldn't really remember the syllabus.
Okay. Not a problem. All right. So getting back to the example I'm constructing right now. Okay. So I'm constructing this example so that vertex B is also going to vertex D, and this particular edge has a distance of 10. Okay, so when you look at this from the perspective of vertex B and D, okay, because both of those would be in set Q at one point, and C is definitely preferred because C has a only has a L value of 1, and B has an L value of 10. So we're going to choose C first, okay? And then we'll look at all the incoming edges to see if we can update the vertices that are going to vertex C through an edge. So this is where A is coming in. Okay, so A is going to vertex C using a very, very costly edge. Okay, so this edge here is going to be, let's say, 20. Okay, as opposed to the edge going from A to B, which is actually pretty short. Okay, so we'll make this 2, okay, a distance of 2. So the interesting part about this really simple graph is it's forcing Dijkstra's algorithm to quote unquote reconsider something that it had discovered already. Okay, specifically the edge AC will be discovered first. Okay, so the first path from vertex A to vertex D is going to be ACD with an L value of A being 21. But then it will find out that, hey, that is not really the shortest path because if A goes through B then to D, then the L value of A would only be 12. So it will have to update itself, uh, when it discovered a shorter path, it will have to update the L value again. Okay, so this graph illustrates that particular point. Okay, so we'll go ahead and run the algorithm on this new graph. Okay, so it's going to be pretty much the same mechanism. I want you guys to look at the algorithm off screen while I use the rest of the screen to display the trace here. So I'm going to start a new sheet, okay, because it's pretty easy to start a new one, and this basically avoids all the confusion. But I'm keeping the same format, okay, just because it's easier to do it this way. I got the right widths already, I got all the right labeling already, okay. So are we good? We are starting with the second graph at this point. So the initialization means anything that is a destination has a L value of 0, and then everything, all the other vertices has an L value of infinity to begin with. So these are all infinity. E prime is empty to begin with, and then the set Q starts with the only destination in this case, which is vertex D. So row 3 is representing how we are initializing all the variables at the beginning of the algorithm. So this only has vertex D itself. So do we have any questions about row 3 of the spreadsheet? How all the variables are initialized at the beginning of the algorithm. So this covers all the statements up to but excluding the while statement. All right, so now we get into the loop. First thing we get into the loop is to ask, is it empty? Nope, Q is definitely not empty. So we're going to pick a vertex out of the set. Since it only has one single vertex, that has got to be the only thing that we can choose from. So V now has a value of D. Vertex D is in variable V to represent that we are now going to explore vertex D, or the incoming edges to vertex D. So we also have to make sure that Q is, we remove the vertex in variable V from the set in of Q, so that we do not re-explore the same thing over and over again. So now we have to look at the edge, or all the edges E that are incoming to vertex D. So in the graph here, we have CD, we also have BD, okay? When you are exploring the edges, okay, so we are talking about a for each loop here in the algorithm, it doesn't really matter, okay, so nothing is prioritized in this case. You can explore the edges in any order you want, okay. So in this case, we'll just go ahead and say, okay, let's go ahead and explore CD first, okay. That will make CW, or the variable W, is going to store vertex C, and then we have to go through the calculation, okay. Okay, so actually I can, no, I don't have enough space. I can do it, because the solution graph is not important at this point. I can just move the window over here. This gives me the room to kind of show you, how the calculation happens. So we want to look at L of D plus D of E, and we want to compare that to L of W. So this makes it a little bit more visual and easier to understand. So for row 5, okay, so for row 5, V is vertex D, which has an L value of 0. D of E is CD, and CD has a distance of 1. So we have 0 plus 1, which is 1. Okay, so I'm going to write down 0 plus 1 is 1 here, because this explains how we got a value of 1 for this entire expression. L of W is L of C, and at this point L of C is infinity. So as a result, the less than relation is true, so we are going to get into the then statement. When we get into the then statement, the first thing we do is we update L of W. So L of W, which is L of C, is going to get changed to the sum that we have just computed over here. So it becomes 1. And we also have to update a few things, because we have to remove any edges coming from vertex C from E prime. But that's pretty easy, because E prime is empty. There's nothing to remove. Then we add the new edge CD into E prime. So E prime now has one single edge CD in it. And we also have to remember to add vertex C to Q because L of C just got changed. So we want to add vertex C to Q so that we remind ourselves and go, okay, let's look at all the incoming edges to this particular vertex because those vertices that are going to vertex C through a particular edge may have their L values changed as a result as well. So that's why we're adding C to Q as a set. So that concludes one iteration of the for each loop. So for the next for each loop, we are looking at another edge that ends up at vertex D. So according to this graph, CD is one edge ending up at vertex D, but BD is the other one. So we want to look at the edge BD in this case, which makes B, which makes variable W storing vertex B in this case. So once again, we want to do some calculations. We want to look at L of V, which is 0, and we want to look at D of E in this case. E is BD, which has a distance of 10, so that just adds up to 10. But L of W is infinity because this time we are looking at B as W, and we can see that in the L values, L of B is still an infinity at this point. So less than is still true. 10 being less than infinity is true. So we get into the then branch, and then we first update L of B to 10, and then we have to remove all the edges that are coming out of vertex B from E prime. So E prime does not have a single edge coming out of B, so there's nothing to remove from E prime, but we also have to add the new edge into E prime. So E prime now has CD as well as BD in it. We are also going to add vertex B to Q because L of B just got changed. So we have to add B to Q so that we are basically reminding ourselves that any vertex that goes to vertex B through an edge may need to be looked into because the L value of those vertices may be changed as well. So that concludes the second iteration through the for each loop. Do we have any questions about this part here? We are looking at all the edges that are incoming to vertex D. Okay. All right. So now because the for each loop is the last statement inside the while loop, we go back to the beginning of the while loop and we ask, is Q not empty? The answer is true. Q is not empty. So now we have to choose a vertex out of Q to explore next as vertex V, as V. So this time we got B and C. We cannot just randomly pick one. We have to pick the one that looks the most promising. So I just want to kind of use this opportunity to mention again, Dijkstra's algorithm is known as a greedy algorithm, and this is why. Because it is always looking at the most optimistic choices, and as a result, it is called a greedy algorithm. Oh, William's typing. In line 6 E prime, is it supposed to be CD and BD? That is correct. Thank you. Okay, I made a mistake here. So it's supposed to be BD and CD. Okay, very good. Okay, good catch. All right, so out of B and C, getting back to selecting which one to become our V, L of C is 1, L of B is 10, so C is the quote-unquote better option. So we're going to choose C in this case. So variable V is going to store vertex C, and we have to remove C from the set, so the set only has B left at this point. Now we have to look at all the incoming edges to vertex C, and there's only one, because from the graph here we can see that there's only one incoming edge from A to C. So AC is the edge we are looking into, and W is A in this case. So now we have to look at L of V plus D of E. L of V is L of C, which is 1, and then the edge is 20. So the sum is 21. And then we have to look at L of W. W is A. L of A at this point is infinity. So now we compare 21 to infinity. 21 is less than infinity is true. So we go to the then statement at this point. The then statement is going to do the usual stuff that we have been talking about. We have to remove all the, first of all, we update. Okay, so we update L of A first, so that it becomes 21. And then we have to remove all the edges coming from vertex A from E prime. But there's nothing here coming out of vertex A, so there's no change to E prime. And then we have to add the new edge to E prime, so that E prime is now CD, BD, and AC. Okay, and I'll make it a little bit wider because I don't want it to interfere with column G. And also, as a result of updating L of A, we're going to add A to the set Q. So is that okay? Is row 8 of the spreadsheet okay? All right, so everything's good so far. Um, there's only one edge going from A to C, so we are done with the for each loop, which also means for this iteration of the while loop, we are done as well. So we go back to the beginning of the while loop and we ask, is Q not empty? Q is not empty, it has got two elements, so we now have to choose which one to expand next. So which one is going to be our next? V is the question. Now C is no longer a consideration because C is not in set Q anymore, so we don't need to consider L of C being 1 anymore. It's only between A and B. So L of B has a value of 10, L of A has a value of 21, so B is the one that we're going to choose. So B is being stored in variable V. So now we have to look at all the incoming. First of all, remember to remove B from the set Q. So Q only has A left at this point. And then we're going to look into all the incoming edges to B, and there's only one, which is AB. So now we have to do the recomputation. Okay, W is A again. So we look at L of V. L of V is L of B, and L of B has a value of 10. Okay, so we look at 10 plus, and then the edge or the distance of the edge AB is only 2. So it's 10 plus 2, which is 12. Right there. And we have to look at L of W. W is A. It just got its value updated to 21, so 21 is L of W at this point. And then we ask, is 12 less than 21? The answer is yes. So this is when things get a little bit interesting, because for the first time, well, let's go ahead and update it first. Okay, so we're going to update L of W, which is L of A, from 21 to 12. This is telling us that we found a path already with a length of 21 from vertex A to a destination. Okay, that's what the 21 is representing. But what this 12 is representing is, guess what? We just found a shorter path with a length of 12 from vertex A to a destination. That's why we're updating L of A. Okay, so after that, we update E prime. So when we update E prime, we are just asking, do we have any edges going from vertex A to some other vertex? Do we have any edges in E prime? And the answer is yes, we do, because we have this edge AC in E prime, so now that has to be removed. So we look into this, and then we say CD is okay, not a problem, BD is okay, not a problem, but AC should not be in this set anymore. Okay, so that's what the for each loop is doing inside the then branch of the conditional statement. The next line says, okay, now that we have removed an old edge from E prime because it is no longer part of a shorter path, let's put the edge that is on the shorter path into E prime. So we update E prime again, but this time we are adding the new edge that we have just looked into, which is AB into the set E prime. And then after that, we also add A into the set Q, but A is already in it, okay? So it really doesn't change Q because in a set you cannot have duplicates. So adding the element A to a set that already has an element of A doesn't really do a single thing, but I am going to use this to represent that, yeah, well, there's an operation, it's just that the operation did not end up changing the value of Q. So that concludes the for each loop to look at all the edges, which is the last statement inside the while loop. So we go back to the beginning of the while loop. The while loop asks, is Q not empty? It is true, Q is not empty. So we go into another iteration of the while loop to pick an element out of Q. Well, since it only has one single element, we have to pick that one. Okay, so we pick A, and then we remove A from the set Q. And now we look at A and go like, okay, let's look at all the incoming edges to vertex A. But guess what? A does not have any incoming edges. Oh, okay. So that means the for each loop inside the while loop has got nothing to do. So then we go back to the while statement again, or go back to the while condition. Q is Q not empty? The answer is false because Q actually is empty at this point. So this concludes the execution of Dijkstra's algorithm, looking at a graph that looks like this. Okay, so the solution of this, okay, if I were to mark the solution using a red line, so I'm gonna move the spreadsheet out of the way so that we can focus on just the solution. So if we are to look at the solution, it has the same vertices. It still has vertex A, B, C, and D. But the solution graph only has 3 edges. One is CD with a distance of 1. One is BD with a distance of 10. And the third one is the edge AB with a distance of 2. This is the solution graph. Okay, the solution graph only has 3 edges, and it shows if you look at the edges of the solution graph, it shows all the shortest paths from all vertices to a destination. Because if you look at it from the perspective of vertex A, it shows that vertex A can get to a destination by going to B first and then from B to D. That is a shortest path from vertex A to a destination. The other two are trivial, so I'm not going to talk too much about the other two. Do we have any questions about Dijkstra's algorithm on this particular graph? Any questions whatsoever? No questions? All right. Okay. All right, so if there are no questions about Dijkstra's algorithm applied to this particular graph, we can potentially move on to the A star algorithm. So I just want to double check and make sure that we're all good with Dijkstra's algorithm at this point. We are good? All right. So we're now moving on to the A star algorithm. Okay, so let me put the algorithm back on screen and scroll down a little bit to look at the discussion of the A star algorithm. Okay, so the A star algorithm is interesting because it makes use of heuristics. So in addition to everything that we used in the previous algorithm, the A star algorithm has a heuristic function represented usually as h The heuristic function is basically taking two vertices, and then it is giving us a value which is representing a guesstimate. Okay, it's a guesstimate from the first vertex to the second vertex. It's basically saying if I have to guess, okay, what is the length of the shortest path from one vertex to another vertex, what would be a good estimate? Okay, that is what the heuristic function is returning. Okay, and when we get to a really concrete example, we can plug in actual values, and everything will start to make sense. Okay, so in order for the A star algorithm to function, the heuristic function has to be admissible. I'm just highlighting the word admissible here. Admissible in this case simply means that the h function has to be less than or equal to the L value of a particular vertex. Okay, to in English, all that means is h has to be an cannot overestimate. That's all. Okay, h as a heuristic, which is a rule of thumb, a simple way to guess something. This estimate, this particular guess, this heuristic, cannot overestimate compared relative to the length of the actual shortest path between two vertices. Okay, so that is what we call admissible when it comes to heuristic functions. So one way to define a heuristic function, if we cannot figure out a good way to define a heuristic function, is to make it zero. Okay, because all the edges are non-negative, so that means the shortest path or the length of a shortest path can at best have a length of zero. So if we plug in h, the heuristic function or the heuristic value between any two vertices to be zero, that's perfectly okay. Okay, it's just that this particular heuristic function has no information in it, so it's not going to help us in any way to make it fast to find a shortest path from a vertex to another vertex. Okay, another difference between the A star algorithm compared to Dijkstra's algorithm that we have just talked about is that the A star algorithm only finds the shortest path between two vertices. Okay, so it cannot handle multiple destination vertices. It can only handle one single vertex as the destination. So are we doing okay so far with the A star algorithm? The algorithm itself cannot handle multiple destinations.
When you say multiple destinations, if we were doing the previous example from A to B, or I'm
Mm-hmm.
sorry, A to D, A to B would be the only solution we would get using this, or would we get the full path from A to D?
Okay, so let's take a look at the previous question. So in the previous question, because we identified vertex D as the only destination, so it doesn't. So for this particular graph, it doesn't make any difference whether we are running the A star algorithm or whether we are running the Dijkstra's algorithm. If they will look about the same because we only have one destination. Is that making any sense?
Yeah, I was just
Okay.
curious if it would stop at B once it found that one and say, "Oh, I'm done. I found one answer," or if it would continue on to D as I guess I
Oh,
kind of look
okay.
at that. I look at it as going A, B, D as two different calculations. So that would be
Okay.
two different destinations instead of the single destination of D.
Um, hmm. So with this one, for the consideration of one versus multiple destinations, um, it only has one single destination. Uh, but the other difference between the two algorithms is Dijkstra's algorithm, at least the one that I presented, finds the shortest path from any vertex to a destination, which means once you run Dijkstra's algorithm on a map, you know exactly how to get from one point to another point on the map. Doesn't matter to a destination. Doesn't matter which point to start with. But the A star algorithm will only find the shortest path from one vertex to the destination. So that's the other difference. In other words, if we mark vertex C as the start vertex and vertex D as the destination in A star algorithm, it doesn't care about vertex A, it doesn't care about vertex B, it only cares about how do I get from vertex C to vertex D, in what is the shortest path from vertex C to vertex D. That's the only concern of the A star algorithm. But the Dijkstra's algorithm will find the shortest path from any vertex to a destination. Is that kind of okay or not?
Yeah, I guess I should have rephrased it to say this doesn't care about any of the points in between your start and destination. It's
It
just looking for
does.
the shortest path to it.
Correct, but because the shortest path is, there are potentially vertices between the start vertex and the destination vertex, so the A star algorithm will still kind of mess around with the vertices between the start and the destination. But we do not necessarily find the shortest path of all the vertices in between. So, okay, so let's talk about another thing first. If we find a shortest path from a vertex to a destination, any vertex along the shortest path, that shortest path applies to everything along the way. The best way to do this is to use an example. Okay. Okay. So this is on the side. So let's just say that using any algorithm, this does not depend on the algorithm that we are using. It has to do with the property of the shortest path. So let's just say that we find that this is a graph, and it has got vertex A, B, C, D, okay, along with many other vertices. I don't really care about the other vertices. I just know that this is the path, the shortest path from A to D, okay? If this is the shortest path from A to D, then we also know, okay, so if this is the shortest path from A to D, we also know that this part here is the shortest path from B to D, which also means that we know that this part here is the shortest path from C to D. Does that make sense?
Yes.
Okay, and how do we prove that? I want you guys to kind of think about proving, because um, this is actually not a very bad, this is actually a pretty good way to apply proof by contradiction. So the theorem in this case, okay, what I'm stating is, if you find a shortest path from a vertex to a destination, any vertices along that path is also going to use a part of that path as its own shortest path. That's the theorem. But how do we prove it? How do we prove that, if ABCD is the shortest path from A to D, then BCD is the shortest path from B's perspective, and CD is the shortest path from C's perspective? How do we prove that? I mean, intuitively it makes sense, but how do we prove it? And in this case, proof by contradiction works. So the way we formulate proof by contradiction is we negate the theorem first, right? So we negate the theorem by saying, yes, we know it is given that ABCD is in fact the shortest path from A to D. Okay, that's all good. However, one of the vertices along this path is not going to use the subpath as the shortest path. So we'll say, let's find that B is the one that says, hey, BCD is not my shortest path. My shortest path is somewhere else, okay? But that cannot happen, because if this path, if this squiggly path actually ends up shorter than BCD, then AB going through the squiggly path to D is also going to be shorter than ABCD, which contradicts what is given, that ABCD is the shortest path from A to D. So this is one of the applications of proof by contradiction. I'm not sure how many of you are kind of following the logic or the reasoning, but it is an interesting way to apply proof by contradiction to prove this seemingly intuitive theorem. Is that okay, or do we have any questions about that? We good? right? Okay, so the next question is, we talk about the heuristic. We know the heuristic is supposed to be admissible, which means it cannot overestimate the actual shortest path. The next thing we want to ask is, okay, give me an example. Okay, I don't really know what we can use as a heuristic. Okay, so this time I want you to think about a real map. Okay, so on the real map, we got a few vertices. We got A, B, C, D, the usual stuff, and then we got E and F on this side. Okay, and remember, in the application of the A star algorithm, we have to identify where we are starting and we are ending. Okay, so we are going to identify A as our starting point, and we are identifying D as our destination. Okay, so the way heuristic works is it will help us avoid exploring vertices that really cannot be on the shortest path. So in this case, the one heuristic function we can use is the actual linear distance between vertices. In other words, we look at this distance here as h of AD. So now, okay, so before that, let me just kind of give you the actual edges. Okay, okay, so we're gonna have some real actual edges over here, but because this one is actually a map and the location of the vertices is the actual physical location, so we can see that HAD, which is measuring the actual distance, direct distance from A and D, it has to be less than or equal to to any path from A to B to D, or from A to C and then to D. Does that make sense? Does it make sense that in an actual two-dimensional map, the direct distance, okay, the linear direct distance between two vertices is a good example of a heuristic function where it is not going to overestimate um, any path or any edges in this case. Is that good so far?
Yeah, I think that makes sense.
Okay, so when you look at the heuristic from F to D, for instance, okay, when you look at DF to D over here, and let me pick a different color so it's easier to identify. So when we look at A to D, F to D, okay, this green line, okay, the distance of this green line is always going to be more than the distance from C to D. So when you look at the green line from C to D, that's always going to be shorter. So when we expand out from vertex A and explore, okay, what are my options? Should I look at this one? Should I look at that one? It would look at F and go like, ew, that is a stupid choice. I'm not going to go there, because the heuristic function is already telling you that that choice is not a very good choice. Does that make sense? So you won't
Because
go.
it's comparing the distance from F to D and C to D?
It is, so from A's perspective, A is going to say, okay, what are my options? So from A's perspective, it is going to consider B, C, E, F as its options. So it's going to put those into what is equivalent to our Q set in Dijkstra's algorithm. But within that set, okay, within that set, it's going to prioritize things that looks more attractive. E is not going to look very attractive, because F is not going to look very attractive either, because the heuristic function from F to D, from F to the destination, not even counting that you have to go from A to F first, that's already looking pretty bad, okay, compared to C. So it will prioritize, the algorithm will prioritize alternatives like B and C that has a shorter heuristic value compared to the vertices, the alternatives that are further apart from like from E to D. Is that okay? So the heuristic function is a way for the algorithm to prioritize what vertices should I examine next. Okay, things that are not really attractive, it's either not going to be considered or it's going to be considered later. Okay, are we kind of getting the idea of why the heuristic function is important? I'll give you another example. I think this one is going to make sense. Okay, I want to go to San Francisco from Sacramento. Okay, from my house. Um, so I got many options, right? Because of the way the highways are connected. So does it make sense for me to go to Tahoe first? That's the opposite direction, right? So if I go in the opposite direction, um, the distance from Sacramento to Tahoe is one factor, but the real thing is if I just draw a straight line from Tahoe to San Francisco, that straight line is already going to look pretty awful. Okay, I might consider Stockton. I might consider um, Redwood City. Okay, even though those may not be very good choices, but they still make more sense compared to Lake Tahoe because Lake Tahoe is not even quote unquote in the right direction. And the reason why we know it's not in the right direction is because the heuristic function, which is the linear distance between Lake Tahoe and San Francisco, versus the linear distance between Redwood City or Stockton to San Francisco. When you compare those, Lake Tahoe definitely does not look attractive at all because it's quote unquote going in the opposite direction. Is that okay? Does everybody kind of get the idea? Are we good or not?
Sounds good to
Yeah.
me.
Okay, excellent. Okay, great. So now we can go into the specifics of the algorithm. We are running out of time, so I'm not gonna do that because it's going to take a long time to explain this one. So I want you guys to read the algorithm before Monday, and I will explain it on Monday as well as to run it on Monday. And this one is a little bit more cumbersome. It has got more. There's more to the algorithm, so it's going to take a little bit more effort to read this one. So I want you guys to read it first um, before Monday, and then on Monday I will construct test cases like what I did today, and then use a spreadsheet to trace through it. Okay. So I'm going to conclude today's lecture at this point, and I'm going to save the spreadsheet. Thank you, Brenda. So I'm going to save the spreadsheet and then attach it to Discord, and then pin it at the top so that way. I'd like to do it this way because it's easier for people to find the files that are relevant on a particular day. So I'm going to push both the graphs, the pictures, as well as the spreadsheet for today's lecture. And Alexander is typing something. Okay. For Dijkstra's algorithm, if we want to program it, how do we basically use infinity? Would we use the max of any variable for infinity? That the answer is yes, because you have to pick a value where whatever is the underlying representation cannot store anything that is more than that. Now that's a kind of an interesting question, because if you choose to use a double or a float as the type of the L value, there are constants defined as infinity, and the comparator can actually compare quote unquote infinity to an actual non-infinity value. So if you choose to use float or double, you can do that. If you choose to use unsigned, okay, any type of unsigned type, then you have to look up, what is the largest value you can use. Or if you use standard integer .h, then those constants are also defined as macros. They have names. So I'm hoping that answers Alexander's question. Okay, great. All right, so I'm pushing the spreadsheet first. Okay, so here's the spreadsheet, and then I'm gonna push the graphs. Okay, so the way I'm gonna push the graphs is, does anyone want me to push it as a Zerno file where you can go into the graphs and make some additional changes, or do you guys just want a PDF? I'm good either way.
I think a PDF will probably work for everyone.
Yeah, I think so too. Okay, so I'll just export it as a PDF. And then the attachment is coming through here. There we go. All right, so you guys might want to open those attachments just to make sure that you can do it. Because if anything needs to be fixed, it's easier for me to fix it now and then re-push it rather than doing it later. I'll go ahead and stop the